So to start off with this expression, we're going to need to create a function in VBA. Just close it. And so we need to create this function. We're going to call it Darcy F. And we need Reynolds number as a double. We need the roughness as a double as well. Entire function will input a double. T1, let's see, we have the equation pulled up here. T1 is going to be equal to negative 2.457 times by log, it's going to be 7 over Reynolds number to the 0.9 power plus 0.27 times by ED, all this to the do I want this in, I'll put this in parentheses as well. Actually, I don't think it matters. 0.27 times by D to the 16th. I believe that is all correct. Let's see, log plus. Yes, okay. Just want to make sure. The second theta is relatively simple. Over Reynolds number to the 16th. The Darcy friction factor is going to be equal to this entire right side times 8, since we just need the F value. We get R8 RE to the 12 power plus 1 over T1 plus T2 to the 5th power, all of this to the 1/12. So that is our function right there. All right, we'll just save this. All right, so we got the function. Now we can start listing off some variables. Our density. 1E3, our viscosity, 1E negative 3. Our length of the pipe is going to be 100 meters, not 199, 100. Diameter is going to be 0.2. We have the roughness is just 1E negative 4. Then our flow rate is 0.1 meters cubed over seconds. We're going to set all of these into variables. We can calculate the velocity by making this equal to 4 times this by Q over 3.1416 times this by the diameter, square that, you'll get the velocity. And then Reynolds number, that's just going to be equal to rho times V times D over mu. So I needed to switch to my school computer because my main computer just didn't want to run VBA, so now you get a different angle, so very exciting stuff. So we need to calculate delta B. The way we do that is we use the Darcy function that we created, input the variables, which would be, again, Reynolds number and the roughness factor. We times it by length, right? What are you doing? Times this by length, times this by v squared, times this by rho, divide this all by 2 times the diameter, and you get this number, which is in pascals. Now we need to calculate how much it would cost to operate a 100% efficient pump to maintain a flow for 2 hours. And we're assuming the electricity costs 15 cents per kilowatt hour. So, what we do first, we need to find the power, right? And let's just set these equal to each other. Find it. Okay. So power. Power is just going to be equal to our answer from a while ago, delta P, times this by Q, the flow rate. And this will be the power, and this is in terms of watts. So we'll set these equal to each other now. I'm not sure if there's an easier way to do it, but this is the best way to know. And so this duration will last 2 hours. And so what we do for this, since we're taking time in seconds, we need to acknowledge that there are 36 seconds in 1 hour, so we just multiply that by 2. We get 7,200 seconds. Pretty simple stuff. So now we can finally get the cost. But first we need to convert this number. Like I said before, this is only in terms of watts. We need this number in kilowatt hours. So to do that, we take the number, and so kilowatt hours, we need to divide it by 1,000, or multiply it by 1e to the negative 1/3, or negative third. That will convert it to kilowatts. We need to divide it by 3,600 to represent the seconds. So now we have this number, and this is the power in kilowatt hours. Kilowatt hours. So now we multiply that number we just got by the duration. We get 7.14, right? And since we need to figure out how much it will cost, the cost for electricity would be 15 cents per kilowatt hour, multiplied by 0.15, you get 1.0708. So this number right here will be the cost to run a 100% efficient pump, assuming that the cost is 15 cents per kilowatt hour.